equals to, just keep the boundary value equals to 1.
We have studied the harmonic function and their properties. So their properties
integration dy equals to 1 over the boundary where modulus of x is less than 1 will be 1, and this will also be 1.
then you may ask. Then
How
I
it
have
is
maximum
coming? So if you
minimum
are
that
unable
is done.
to do this in the
Then I have
Cartesian
reached the
coordinates, so I
problem
am giving you an
in
example.
Cartesian coordinate.
I was integrating from 0
Then
to
I have used
5.
the Fourier series to solve the Dirichlet problem on the interior of the circle, on the exterior of the circle. I am going to complete it today. Then we have studied the Poisson kernel and Poisson formula.
R square minus 2.
Then we have studied the electrostatics example. We have also studied the Heaviside function that I am going to use in the Green function, and we have also studied the delta function, which I am going to, so which was not the part of your syllabus, but still we did it because we wanted to use that thing. Next, what is left? Still, we are left with the Perron's method for the existence of the solution of the Dirichlet problem. So this is more theoretical, not very mathematical. Then we have Green's function, so it is very mathematical things. Then we have eigenvalues method, or you can say that eigenfunction method to solve the Dirichlet problem. So still we are left with 3 topics, I think, and it would take 2 weeks because this to topic is really big. I will try to complete it soon, but I can't say anything. So the next week and the next week. So the next week is 9th, 10th, 11th, 16th, 17th, 18th. So still we will be just running in the unit 3, and I will start your unit 4 in the just I would be able to take only one class before the exam. So only unit 3 will be the aim of this exam because it is not possible. Unit 4 will take less time as compared to unit 3 because we are very much aware of the Poisson's kernel, so we will be able to solve the fundamental. We have also seen that Heaviside function and the delta function, so which we are going to use in the Duhamel's principle to solve an inhomogeneous problem using a homogeneous boundary condition. So that would be easier as compared to this unit. And wave equation, we are already much aware of the wave equation. That was our favorite topic. Yeah. Roberto, did you try to solve the integration which I asked you to solve? Okay. Okay, so let's start the exterior Dirichlet problem for a circle. I have a question, whether you were able to solve it or you did not try. Was it difficult or you did not try?
I did not try.
Okay, then fine, because if it was difficult, then I could do. Okay, so you are confused about why I am making this integral from the summation. Okay, so just let's rewind ourselves the previous thing. You could see that using the Fourier series, we wrote the solution of a Dirichlet problem on the interior of a circle in this way. Is it clear how I write it? So here you can see that we used a boundary condition, and using that boundary condition we got a condition on theta, that is when theta is integer multiple of pi, then the solution will be written in this form. Another solution will be zero solution. So theta is the integer multiple of sine. You are going to vary theta. Now when you will be taking theta equals to pi, you will get one solution. when you will be getting theta equals to 2 pi, you will get another solution. When you will write theta equals to 3 pi, you will get another solution. Now we have to write the complete solution of the equation. We have to write the complete solution of the equation. Is it clear? So I am talking about the complete solution. So if we have 1 to n number of solutions, so what will be the complete solution of a given PD or given ODE? The superposition of those solutions, the summation of those solutions. Like just let me give you a very basic example, then you can understand. d2 y over dx square plus y equals to 0. This is a ODE. Okay. Now I am saying that if you are taking y equals to cos x, so please check whether it is satisfying this ODE or not. Roberto, please check whether this is satisfying this ODE or not. Say it is y1. It is satisfying, okay. And then y2 equals to sin x. So it means y1 and y2 both are the solution of the given ODE, is not it? So what will be the complete solution of this ODE, or you can say general solution of this ODE? So you will say that the general solution of this ODE is the summation of these two solutions, or you can say the superposition. When we talk about the superposition, so superposition means the constant multiple of these solutions, the summation over the constant multiple, like c1 y1 plus c2 y2, and where c1 comma c2 is belonging to the real number set, like these are constant. So this is the complete solution of the given ODE, is not it? Now, is it clear what is the concept behind this writing the complete solution? So in the same way, if you have n equals to 1, so one solution will be u r comma theta u r comma theta will be 1 over pi 0 2 pi f pi plus 1 over pi 0 2 pi f pi, n is 1, so r over n cos phi minus theta d phi. This is one solution, say u1. In the same way, if you take n equals to 2, then you will be getting another solution u2 r comma theta. Now this is fixed in each of the solution. This is fixed. Only this is varying. So we need to take the superposition of this part to write the complete solution of the given Laplacian equation in the inside of a circle. So that's why I am doing this summation. Now we are writing the solution in the form of a summation, like you are varying something. So it is not a closed form solution. You still have to take the summation of a series. So our aim is to write to get rid of summation. Now to get rid of this summation, we need to follow some techniques so that we can write a closed form solution. That is, we can write the unique solution. We don't need to take the summation over the integers. So that's why we are using some kind of trigonometrical approach to write the solution of the Laplacian equation in the circle, inside of a circle. So this is just a technique, like it is not developed by me, it was developed by an author, and everyone is following this technique because the Laplacian equation is arising in a number of physical phenomena, So when we write the solution of that physical phenomena, like suppose one equation is Euler equation and another equation is Laplacian equation, that is representing the potential of electrostatic, that is the potential of an electron which is coming from the infinite. So this will be a system of, now to solve the last equation we can use this method, but every time when we are writing the solution of even a single equation, we need a unique solution. We don't want to add the summation because it is really difficult. You don't know what you will be getting after adding till the infinite, because this is an integer. So that was our aim, that we are going to write the solution of this Laplacian in a closed form. So when we use this method and then we arrived that this summation term c plus is coming as this form. So this c, I chosen this c is equals to this part, basically this summation part I choose c, and this s. So if c plus is the resultant which I will be getting, so the real part is going to be this c, it means the real part is going to be this summation. So I followed this technique and then used the formula like summation x to the power n modulus of x is less than 1. You already know from the real analysis that the summation is going to be x upon 1 minus x. So using that formula we arrived that this c is equals to this. It means we now get rid of this summation. We are getting a particular, we are getting the value of this sum series, because there is always, if the series is convergent, so you are able to write the summation of that series. Is not it? If this happens, so in that case series is convergent. Is not it? If this was greater than 1, then in that case we can't say anything because the series may diverge as well. So since this was less than 1 inside the circle, so series was convergent, and because of that we are getting a particular value of that summation. So we are using a lot of real analysis and a lot of physics, everything like that. So I did not explain this part in a very detail, because if I am going to real analysis, then it was going to expand our discussion. So since this series is convergent, so we are able to write a particular value for this, not particular value, I will say a particular function for this summation, a particular function for this summation, and in that case we get rid of the summation and we have a particular function. So it means we have a unique solution. We don't need to take the summation over this. So that was a closed form solution. Now when we write the closed form solution, then we can see that this integral, this kind of integral like a to b of with a function phi, and this is function of two variable d phi x comma phi. So this function is known to you, this function is known to you because this is the boundary condition, is not it? So we say that this function is weighted by this function. So basically using this method we arrive at a solution where this function that is known to us, because this is given as a boundary condition. So what I was saying, the boundary potential weighted by the Poisson kernel. So I say that this is your Poisson kernel, and the boundary function, basically since this is a solution of the potential equation, del 2u, this is known as the potential equation or electrostatic equation or somehow steady temperature in a rod. So this is a solution of a potential equation. So if f is the boundary potential, like the value of the potential at the boundary, so the boundary potential is weighted by this function, and this function we give it a name that is known as Poisson kernel. Like have you read about the Fourier series and Laplace equation, where we define the Poisson kernel? There is a particular topic. Now Fourier series, no, where we talk about the kernel, Poisson kernel and all. There is another branch of mathematics where we solve a series. Fourier series, no. Just let me. What is the name? Can you suggest me? That is also the part of it. I have that name in my mind, but I just unable to say. So there is a we talk about the solution of the differential equation using that method, and then we talk about the kernel, if you remember. So that is basically, this concept is coming from there. I will get the name, then I will write. I have in my, but I'm not, it is not coming to my tongue, so sorry for that. So this is the Poisson kernel, and this is the weighted function for this boundary potential. So this is the definition of, now every time when you will be writing the solution of the Laplacian, whether in cylindrical coordinates, whether in spherical coordinates, you are going to get this Poisson kernel. Is it clear, Roberto? Okay, I know sometimes language barrier, because of the language barrier, it might be difficult, but I tried my best. Camilo, is it clear to you?
Yeah.
Okay. Now we are coming to the next part, and the solution of the exterior Dirichlet problem is going to be just opposite to the interior Dirichlet problem. So would you guys tell me what is the value of logarithmic of x when x tends to infinite? What is the value of logarithmic of x when x tends to infinite? Is it defined or not defined? Not defined, yeah. So the logarithmic at x tends to 0 and x tends to infinite is not defined. So that was the concept which we are going to use. So this is your Laplacian, and this is the boundary condition. What is the figure for this? So my circle is so bad. Sorry for that. So if this is a circle, and this is a circle of radius a, so this time we are defining the problem on the exterior of a circle, and the boundary is now this. So basically the circle is defined, the problem is defined in this region, and the problem is not defined inside this circle. So this is known as exterior Dirichlet problem, where the boundary is bounded. This, now you can see that the boundary is bounded because it is the circumference of a circle. It is a circumference of a circle, so it is bounded. However, the problem is defined outside of that boundary, outside of that region. So now r tends to infinite. So since we are going to write the solution, so the solution should be bounded as r tending to infinite according to our necessity. This is the necessity of the problem, that the solution should be bounded even when r tends to infinite, because we are defining the solution on the exterior of a circle. Now if so to write the solution, what we did, firstly we write, if I am wrong then you may tell me, is it? Oops. Yeah, it is 1 over r square is there. So this was the Laplacian in polar coordinate, because every time when we have the boundary condition on r and theta, so we have to have the system in that coordinate system. So it is polar coordinate. Again the periodicity condition come because every time when it will be completing 2 pi, it has to be the same value. Okay, so if you use the method of separation of variable, we have 3 kind of solution. When one kind of solution was including C1 logarithmic of r plus C2 logarithmic of r to the power n lambda, and then C3 cos n theta plus C4 sin n theta. That one solution was this. Another solution was C1 logarithmic of r plus C2 and then C3 cos n theta plus C4 sin n theta. Since we already have calculated the solution of this system using the separation of variables, so I'm not going to explain that again. You already know the same thing. And the one solution was C1 C1 r to the power n plus C2 r to the power minus n an cos n theta plus bn sin n theta, and since this n was an integer, so we have to take the summation. Now again you can see that in the previous problem the r equals to 0 value was coming inside interior of a circle, that was the center of a circle, so we could not take this to proceed. Now again when r tends to infinite, the solution must be bounded, so because of that we cannot take this. Now we are left with only one. So again, since u must be bounded as r is tending to infinite, so this should not be accepted, is not it? So C1 should equals to 0 because u must be bounded as r tends to infinite. So just adjusting these constants, so u r comma theta is equals to summation n varying from 0 to infinite C2 r minus n an cos n theta plus bn sin n theta. Now send this C2 inside the and take it as an and take it as bn. So we know that this n is an integer, so it is varying on the integer value, like n is belonging to j union 0 you can say. So some people consider 0 as an integer, some people does not consider 0 as an integer. It is just their choices, but we are taking 0 here. So at n equals to 0, this is going to be 0, is not it? And this is going to be 1. Okay, so only we are left with an. So without loss of generality, we can take a naught equals to a naught over 2, and then this equation can be written as the variation will be from n equals to 1. I would like to point out that to write this n belongs to z union 0, I already have used the periodicity condition. Using the periodicity condition, we wrote that lambda is going to be n pi, is not it? Theta, like lambda theta is going to be multiple of n pi. So this n is writing, so I have already used the periodicity condition because you are aware of all those things. You already have followed those steps in the previous problem. Roberto, would you please tell me, like when you are reading the topics from the previous, so are you getting the concept of those topics or not? Yeah. Okay. I Okay. So because it might be possible that in the class it is not very clear because what I am telling. But when you will be studying by yourself, so is it clear when you are studying by yourself? Okay. Mm-hmm. No, you can tell me. I understand your English. Don't worry. Mm-hmm. You are talking about this yen? Mm-hmm. Mm-hmm. I'm not getting. Would you please tell in the Spanish so that Kamini can translate? Just say in the Spanish and then. Mm-hmm. What he is saying exactly? Samito?
He was saying that the term r to the power minus n in some books are write like uh, l to the power n over r to the power n, something like
Yeah, yeah, that's right. That's right. So don't worry about that. I am coming to that point. In some book, you might be getting it is written as 8 over r to the power n or l over r to the power n in some books. So that is coming from the Fourier series. Okay, let me come to the point. That is the next step which I am going to follow. But before that, again, just go to the previous problem. This was the exterior of a circle. If we were talking about the interior of a circle, then what we got? We got r to the power n. And now here, what was our geometry? The geometry was that we were defining a circle of radius a, and the problem was defined. Okay, on the problem was defined on the interior of a circle. Just remind yourself about the book I am going to tell you. So in the book you might have gotten it r over a to the power n, and if I am taking this l is the radius of the circle, so it might be because when we are taking the boundary condition u of a comma theta equals to f theta, then we are getting a to the power n here, is not it? And then when we are using the property of the Fourier series, then we are getting the value of an is equals to, just pass this a to the power n to the denominator, and when you will be substituting an here and bn here, so it will be rn over a to the power n. Rn over a to the power n. So we can write it is like r over a to the power n. Is not it? This was the interior of a circle. So we are using the Fourier full range Fourier series for the boundary condition, and then we are getting this, and then in the last you can see that I wrote it. Is not it? And then I took r over a outside of that, and then I write r over a to the power n. So you are talking about this thing. In the same way, when we will be going to the exterior of a circle, now here r to the power minus n is coming. So here we will see that it will be coming like a over r to the power n, because this is basically 1 over r to the power n. So we will be getting a to the power n term from the full range Fourier series, and then we will write in that way. Is it clear? Yeah. Sorry, my friend. It is difficult for me sometimes to understand. So the boundary condition, u a comma theta equals to f of theta gives u a comma theta is equals to f theta when we take at the boundary of the circle. So this is the boundary of the circle, is equals to a naught over 2 plus summation. This is a very long weekend for all of you, like Thursday, Friday, Saturday, Sunday. You have 4 days. So it is my request, please read all the topics thoroughly. Please read all the topics thoroughly and discuss in your group. And if you have any doubts in any of the topic, so please discuss to me in the coming class. Okay? I don't think that in any of the derivation of the problem you might have difficulties, because I have tried to explain, I have tried at least to explain it in a detailed way. So a to the power minus n, an cos n theta plus bn sin n theta. And again, this is a full range Fourier series. This is again a full range Fourier series. It is my request that please go over the topic of Fourier series and Laplace series once to remind these things. That is a very small, like it is only of 10 pages. You can go over that and just read these topics. So it is a full range Fourier series in f theta, where a naught is equals to 1 over pi integration 0 to 2 pi f theta d theta a to the power minus n, an is equals to 1 over pi integration 0 to 2 pi f theta cos of n theta d theta, and a to the power minus n bn is equals to 1 over pi integration 0 to 2 pi f theta sine of n theta d theta. Okay, so just pay attention to this term, just pay attention to this term. I am passing this term to here. Again, just pay attention to this term, it will be coming in the denominator. Is not it? So it can be simply written as a to the power n over pi integration 0 to 2 pi f theta cos of n theta d theta is equals to a to the power n over pi integration 0 to 2 pi f theta sine of n theta d theta. Now we are going to use the value of an, bn and a naught in this solution. Say this is your equation number 12. So u of r comma theta. This is not the solution, sorry. This is not the solution. The solution is here. Okay. Now you can see that this theta is variable, so if we change it to the phi, it does not make any change in the solution. We can change theta to phi, x, whatever he wants, any variable.
Sorry for the late joining.
You have any other class?
I had a homework to turn in.
Mm-hmm.
So, no, not from this class, surprisingly.
Okay, so here you can see that it is r to the power minus n and a to the power n. So can we write it like a over r to the power n? And similarly here this can be written as a over r to the power n. And we can also pass this cos n theta to inside of this because it is independent of theta, and sin n theta to inside of this integral. So this will be 1 over 2 pi integration 0 to 2 pi. This integration is coming over all the terms, so just be aware of that, because this integration is coming all over the term. Oh, sorry. My mind is just time. I am already writing this integration here. Okay, so f phi d phi plus summation n varying from 1 to infinite r over a over r to the power n integration 0 to 2 pi cos n phi plus sin n phi. So we can write it like cos phi minus theta. Cos n phi minus theta, since cos minus theta is going to be cos theta. So whether you can write it theta minus phi, whether it is you are writing it phi minus theta, it will not make any significance change. Okay. Now just take this integration outside of all the term. Pi is also here, 1 over pi. My calculation is very bad sometimes. I can make a mistake. You are here to correct it. So just take the integration 0 to 2 pi f of phi plus summation n varying from, again f of phi is common in all of these, is not it? So even we can take this f of phi outside of this. We are left with 1 over 2 plus summation n varying from 1 to infinite a over r to the power n cos of n phi minus theta of phi d phi. Again we can see that we are not getting a closed form solution, rather than we are getting a solution which is varying over the integer, which is the summation of a solution, summation of a set of solution, is not it? So to write a closed form solution, we are again going to follow the same technique what we followed yesterday. I am not going to derive it thoroughly. I will just give you an outline and then you can see how it follows. So if you will be assuming C equals to this term and S is equals to sine of this term, and then you will be writing c plus iota of s. You will be getting summation n varying from 1 to infinite a over r e to the power iota phi minus theta whole to the power n. Is it clear?
I have a question about this. I'm reading the notes. So the exterior Dirichlet problem can be thought like solving the Laplace equation, like outside of the boundary.
Yeah.
Like,
but the function is continuous at the boundary. That's why we have the boundary condition, because the boundary is always bounded.
okay.
Yeah.
Yeah. But we are working on points that are like very close, but in the exterior of the circle, right?
Yeah, exactly. So,
Okay.
so you are right, but have you noticed one thing? When we are talking the exterior Dirichlet problem, now we are not taking the boundary at the infinite. We are saying that the boundary is bounded. It means we know the boundary, is not it? So that's why we are taking this as a boundary. Because if we are increasing r and r tending to infinite, then we don't have a boundary there because it is unbounded. So we have to consider a bounded boundary. So that's why we are taking the circumference of that circle or some circumference of that disk as a boundary. And in the same way, if you will be working in 3-dimensional, so the surface of that is fair. If you are in 2-dimensional, the circumference of circle or some circumference of disk, if you are in 3-dimensional, then surface of that is fair, is going to work like a boundary.
Perfect.
So A is greater than R or A is less than R. In this case, what is true?
A is less than R, the second
one. So in that case, A over R will be less than 1 because R is unbounded and A is known. R may tends to infinite, but A is a fix. So again, this term is less than 1. Modulus of e to the power iota theta is less than 1. Again, this is a series whose term is less than or equals to 1. So this will be a convergent series. Again, the same procedure you will be following, and you may proceed like you can write this is a convergent series. So summation n over 1 to infinite of this n is going to be x upon 1 minus x, and then you will separate the real part and the imaginary part. So the real part is going to give you the c. So c will be I have solved one of your assignment problem because in the assignment I have given that write the Poisson kernel for the exterior of a circle. So you are done. You don't need to solve it. You will just copy paste from here. So minus 2a over r cos of phi minus theta plus a square over r square. So this is your C, and this was your summation of n varying from 1 to infinite a over r to the power n cos of n phi minus theta. So we are able to write the closed form for this summation. So solution can be written as, for the solution you have to add here 1 over 2 u r comma theta is equals to 1 over 2 pi integration 0 to 2 pi r square minus a square f of phi over r square minus 2ar cos of phi minus theta plus a square d phi. So this term is the Poisson kernel. Oops. So this term is the Poisson kernel, and this is the Poisson integral. It means the potential at the boundary is weighted by this Poisson kernel. The potential function at the boundary for the exterior Dirichlet problem is weighted by this Poisson kernel. So this is the thing which I have written in your notes. You just need to go over that, and yeah. So let's proceed with the application of the Poisson kernel. What is the mean value property? Can anyone tell me the statement of the mean value property? So, if U is harmonic function, do you guys remember that when I was writing the mean value property using the ball, so I was writing that Ux is equals to 1 over volume of that ball of radius r, and then the value of U at the boundary, is not it? That was the mean value principle. And for the circle it was 1 over 4 pi r square, the value of U at the domain, if you remember.
The value on the inside of the disk is equal to the average on the boundary, right?
Exactly. So this was the exact statement I have written in the notes. So I was just writing how it is coming from the from this derivation. I'm going to tell you. So if U is harmonic, in a disk, that was basically the property of a harmonic function, mean value property. If U is harmonic in a disk and continuous on the boundary, continuous in the closed disk. So continuous in the closed disk means it is harmonic in the disk, so for sure it is differentiable in that disk. Continuous in the closed disk, it means it is also continuous on the boundary, because we cannot talk about the differentiability on the boundary. The disk, then the value at the center equals the average of the boundary values. So just let's remind ourselves one formula. Here it was 2 pi, is not it? Is it? So what will be the value of this function at r equals to 0? What will be the value of this function at r equals to 0? This was the Poisson kernel even for the interior and for the exterior of the circle, is not it? So what is the value at the center?
One over 2 pi.
Am I making a mistake? It should be 1 over 2 pi here. Oh, so it is asking about the value at the poison kernel, not the poison. Oh, poison kernel. So I think I am making a mistake. Let me go through the book, because the value of the poison kernel should be. It is saying that it should be 1/2 pi a. Just wait for a minute. I don't know. With the Cartesian coordinate I am getting, but with the polar coordinate I am not getting. With the Cartesian coordinate we have p x comma y is equals to a square minus modulus of x square over 2 pi a modulus of x minus y whole square. So modulus of x is less than a and modulus of y is equals to a. So if you use harmonic in a disk and continuous in the closed, the value at the center equals the average of the boundary values. This follows Poisson kernel at the origin equals if we consider, so we take origin means x equals to 0 and y equals to a, so a square over 2 pi a modulus of a square. So here I am getting, but why I am not getting here? Can anyone suggest me something where I am making a mistake?
Maybe something in the initial conditions,
No.
or some derivatives, something like that. The modulus, I don't know. That's my
Are you talking about the initial condition? Because from the Cartesian coordinate I am getting, but from the polar coordinates I think r equals to 0.
x equals to
X equals to
r.
0 will be the center here. In the Cartesian coordinate, when we will be taking x equals to 0, it will go to the center. And automatically we have to take modulus of y equals to a, because that is the boundary. So in this case it is true.
But x equals to r cosine theta, right? No, x. Yeah, x. what if we substitute x equals to r cosine theta and y equals to r sine theta in the solution P of x comma y. If we substitute that, then you get r squared multiplied by cosine squared, and then in the denominator part you get 2 pi a. You can that's x minus y dot x x minus y, the modulus squared is equal to, yeah, and then square that, and if you square that you can yeah, you can use the binomial. R squared, 2r squared, y 2r squared.
Would you please go over that, and I will also go over that. We can proceed with the applications. I think I'm making some mistake. There is something very thin and I am doing a mistake. I need to find out that mistake because from this it is clear, but from the Cartesian and from the polar coordinates I'm not getting. No, I don't have a mistake. I have everything is correct. I am saying that I am not finding that at center we have to take r equals to 0, but we also have to put some restriction on theta. So in that case we will be taking 2 pi a. So it is not a mistake. Everything is correct. Only the mistake in my concept to tell you. So I need to again go over that, because from here at center x equals to 0 we are getting the Poisson kernel equals to 1 over 2 pi m. But from the Cartesian coordinates I am just getting 1 over 2 pi. It means there is something. So I will do that. Like you can also think about that and
but if the circle is centered at A, then you get 0, right?
Center is at center is not at A.
0,
A is the
yeah.
radius. A is the radius, so that cannot be center. Is not it? And r is varying, so that's why I was taking r equals to 0, because if r is 0 then we are going to get the center, but we also have to take some condition at theta, I think. For the time being, just proceed with the Cartesian coordinates and think about that. I will also do, and then we can talk about that. What was the problem here? Okay. So this follows directly from the fact that the value of the Poisson kernel, this is Poisson kernel in Cartesian coordinates. So the value of the modulus of x is less than a and modulus of y is equals to a. So the value of the Poisson kernel at the origin, that is p of 0 comma y is equals to a square over 2 pi a modulus of y square. So modulus of y is a, so that will be a square over 2 pi a square. So that will be 1 over 2 pi a equals 1 over 2 pi a. And this, you can see that this is the average of the boundary value, because the circumference of a circle is 2 pi r. So furthermore, if u is harmonic in the exterior of a disk continuous up to the boundary and bounded, then it is given by integration of the boundary value with respect to the Poisson kernel, and then we have limit. This is for the exterior Dirichlet problem. because in the exterior Dirichlet problem, modulus of x is greater than a and it may goes to infinite ux that is equals to average of u over del d alpha. And also when you will write the Poisson kernel in the term of the Cartesian coordinates, then you will be getting limit modulus of x tends to infinite e x comma y is equals to 1 over 2 pi a So from here we can see that u is harmonic if its average value over any circle equals the value at the center. So the by mean value principle, this was the average over the circle, and by the interior Dirichlet problem using the Poisson kernel, we can say that this is the value of the Poisson kernel at the center. So it is the same way whether you are writing whether we are using the mean value property or you are solving a Laplacian equation to write the Poisson kernel, and in that case you can write the average value over that circle. Now strong maximum principle. So let U be a harmonic in a bounded open region D. U be harmonic. It means Laplacian of U equals to 0 in a bounded.
I have a question. How do we call the functions that satisfy the Poisson equation? We call them hyperharmonic or something.
Harmonic, yeah.
Also harmonic.
We call that a function. This is the Laplacian. This is the
harmonic is for Laplace equation, right?
Yeah, Laplace, you can say that harmonic for the Laplace equation, and this is the definition of the harmonic function, that its summation of its second order derivative with respect to all independent variable is 0. So that is the definition of the harmonic function. So that's why we every time call that the solution of the Laplace equation is harmonic.
But I was asking for the name of the functions that satisfy the Poisson equation. Do they have like a name?
Poisson equation, are you talking about this equation?
Yeah, I'm asking for the solutions of the Poisson equation. Do they have like a name, a known name?
No.
Okay. I thought they have like a.
Yeah, no, it is not like that.
Similar.
It is not that the harmonic was given on the name of the solution of the Laplace equation. No. Most of the functional analysts use this kind of function to analyze a lot of things like their function in the Sobolev spaces and on all over the spaces. That's why this is the function which satisfies this kind of property. If it is the function of n variable, say it is function of 3 variables, then it is satisfies this property. So, and this property is known as harmonic function. Now, in the physical phenomena, in most physical phenomena, a lot number of physical phenomena, like if you remember about the electrostatics, electron was coming from infinite, then we could write del u equals to 0. A a number of physical phenomena are formed by this equation, so we call it a Laplacian. Like we call this operator as the Laplacian operator. Now the solution is going to satisfy this term, it means the solution is going to satisfy. So basically we call, since this is the property of a harmonic function, so that's why we call that the solution of the Laplacian equation is harmonic. Is it clear?
Yes, perfectly clear.
Okay. There is no relation between that we are writing the solution of a Laplacian or we are writing the solution of a Poisson equation. That's why we are calling it some name. We are giving it some name. No.
The general solution of the Laplace equation are green functions, right?
The general solution of the
Well, nothing. I'm thinking about like I'm thinking about the general solutions of Laplace equation, but there's the general solution are harmonic functions. So it doesn't make any sense to ask the question because all of the functions that are harmonic solve the Laplace equation.
Would you please repeat your sentence again?
No, I'm just thinking about the general solutions. Laplace equation in 3 dimensions and in 2 dimensions. But the general solution of the Laplace equation, the most you can say is that they are harmonic functions.
Yeah.
There's no more to it. There's no more to it.
There is no?
There's no more to it.
Okay.
Yeah.
I would like to I have explained that example before. So suppose I am writing this Laplacian equation. If you haven't given any of the boundary condition, so it is a general Laplacian equation, and you can write that, you can see that this is a harmonic function and this is the solution of this Laplacian equation. But when we are using the Dirichlet condition, when we are using the Dirichlet problem, every time we are getting the solution in the form of cos theta and sin theta, is not it? So this is also a harmonic function. Here, this Laplacian problem has a solution in this form, but it is not fitting in the Dirichlet boundary condition. It might be possible that if you are choosing a certain kind of boundary condition, then this will also be a solution, but it is not fitting in the Dirichlet condition which we have defined, because when we are writing the solution of a partial differential equation, that solution should also satisfy the boundary condition. So for our problem it was not the solution, because every time we choose the boundary condition like u x comma 0 equals to fx and all other are 0, so it is not going to satisfy this, because at u 0 comma y was defined 0, but it is not defined 0, u 0 comma y equals to 0, so it did not fit in our domain of boundary condition. So that's why, but still it is a harmonic function, it is a solution of the Laplacian equation. So you may form a number of Laplacian equation, you may form a number of harmonic function which is solution of the Laplacian equation, but you have to particular about the solution which is satisfying the given partial differential equation and which is also satisfying the given Dirichlet condition or Neumann condition. Is not it?
Yes.
Okay, for the time being, I would like to ask you to solve a problem very quickly before proceeding to the strong maximum principle. Don't leave the class. You have to solve and you have to tell me the answer. So this is a Newman problem because the boundary condition is defined on the derivative of the dependent variable, and it is in two-dimensional because we have two variable r comma theta. So you already know the solution. Just apply the boundary condition and tell me the solution. You have 10 minutes. You already have the solution. You just have to apply the boundary condition. What are you getting?
This has a serious solution, right?
Sorry?
This can be written as a serious solution.
Yeah, so what are you getting?
I'm stuck.
Are you guys getting a Fourier series like G theta equals to summation n varying from 1?
Multiplied.
Are you getting this?
Yes. Yes.
Yeah.
So this is a full range Fourier series. So again you will be using the concept of full range Fourier series. This is going to be 1 over pi integration 0 to 2 pi cos of n theta z theta d theta. Is not it? And then again you can substitute, but in this case you will not be able to write it in the form of Poisson kernel. So please go over that, and this is your homework. Like, it is very simple, everything is same, everything is same. Are you getting this thing? So just substitute the value of this, the value of this. A naught over 2 is still undetermined to us. So just substitute, you will be getting an equation in A naught over 2 plus summation of this thing, and then try to find out the value of the summation. Please do that. If it is not possible, then I will give you the solution. It is very easy. It is similar to the previous one. Okay. So let's stop the class here, and then we can start the green function either or the Perron's method in the next Monday class.
Okay.
Okay, bye.
Bye.